Okay, so after this very interesting lecture by Professor Eden, where he defined all the how to make the design decisions very fast and very systematically, and also in a way that it promotes the solution towards the optimal solution, even though we are not doing any optimization. What I'm going to do now is take that design and say, what are the next steps? And then based on the next steps, what we need to improve. So our reference point is that we have done a rigorous simulation using the design that we have got. And now we want to do economic analysis, and we are going to use a tool called Econ. Is a much simpler tool than Icarus or other tools that you get from commercial simulators. We will do sustainability analysis that are programmed in CAFD, and then LCA with a tool LCSoft, and safety analysis, which is also programmed in. So let's see, and then based on this, we will define hotspots where possible improvements can be done. So our starting point is that then this is what we want to achieve. This is the objective. We have a base case process simulation based on the design that we have done. And the base case simulation gives us detailed mass and energy balance, process constraints, all of these. So using the results, we need those simulation results so we can do the economic analysis, sustainability analysis, LCA, safety. And then based on these, we will identify potential problems, maybe decrease the waste, measures for comparison, all these things we will check. So if we look at the steps in terms of 12 tasks, we did up to 7, task 7, which was the simulation. And we discussed before now, tasks 4, 5, 6, 7, and very detailed in 7, how to do all the design decisions so we can reach 7. Now, once we have done the simulation, task 8 comes in with respect to the costing, sizing, then the economic analysis, then the sustainability analysis, LCA, and then task 9 is just overall representation of the results and target definition. So this is where we are now. So let's look at now the things about the model for sizing, costing, economic evaluation, LCA. These are nothing new, so I'm not going to go into the details of the model. I'm going to discuss more on how to do those calculations. What is the best way? What are the best way to provide the data that is needed? And what is the best way to interpret the results? The models are not made by us. We have just collected the best set of models we could find. So first, I will show you what the table shows is the design, the rigorous design based on the methods that Professor Eden has talked about for the distillation columns, for the choice of the reactor conditions, for the specification of the heat exchangers, compressors, pumps, etc. So just one thing about the driving force-based distillation column. What we do is after the binary pair of compounds that are the key compounds in the multi-component mixture separation, and since there are no isotopes, for those key compounds, we calculate the driving force, and based on the driving force, we find out the feed location. And this actually represents the minimum reflux, not the minimum pinch point reflux, but the minimum reflux that could be used. And that minimum reflux then corresponds to the maximum driving force that we are using. So what it means is that at that driving force, at that minimum reflux, giving us the two products, and we specify the two products recovery, the cost of operating the column would be the minimum, because maximum driving force is inversely proportional to the driving force that is used. So that is how we do the design very fast. As soon as we know which binary pair it is and what is the relative volatility, we can immediately find the corresponding number of stages, the feed location that gives the product that is required. Even though we have not done the optimization, if one does an optimization, one would come very close to what we are giving. So at this point, let's say we have a full set of decisions related to the design variables, and we have verified through simulation that the products we want, we get. What we have not done now is, can this design be further improved? But before we can do that, we need the analysis. So the specifications gives us allows us to do the rigorous simulation. We do it in any simulator. We are using Pro2 here. And after the simulation, we will pass this information that you see on the input data, like raw material and product flow rates, raw material product prices, equipment sizing parameters, heat duties, utility types, prices. The prices have to be given separately, but all the information that is generated by the simulator will be passed into Econ, and Econ then will do the calculations for the capital cost, for the utility cost, operating cost, and the economic evaluation, which you will see later. So how do we do the costing and the sizing and costing rather? First, we prepare a list of unit operations that are in the flow sheet. Then for each unit operation, at a design that matches the desired input-output condition that is already done, because the simulation is done at that design, we perform the calculations for the sizing parameters. So for example, we have designed the distillation column with number of stages, reflux ratio, feed location, product purity, all of that. The simulation results of all of these then are used to calculate the sizing parameter, which is the diameter and the length of the column. Okay, so for each unit operation, we need to calculate then, using the simulation results, the sizing parameters. Once the sizing parameters are available for all the unit operations and all other data for the raw material for the product, we do the cost calculation, choosing a cost model. And in our tool, Econ, we have the latest version of the, let's say, the Guthrie based cost model. So that's the one that is used. But in addition to this step 1, 2, 3, you will see that additional design decisions need to be made. Even after we have done all the design decisions. For example, if we are taking a pump or a compressor or a heat exchanger, even a column, we have to choose the type of equipment. So there are different pumps, there are different types of compressors, heat exchangers, we have to choose that. We have to choose the choice of pressure. This we have already made, but the pressure could be something that we need to look at again, because the pressure will determine the thickness of the material of the equipment that we are going to use. And also we have to choose the material. What kind of material will be in the reactor, in the heat exchanger, etc., and other parameters specific to unit operations that are being used. So there are many more decisions that will need to be made. So how to calculate the sizing parameter and how to do their, how do their values influence the cost estimates and also sustainability? This is a question that will come up and we will look at that. We will also see how to make the decisions on material selection, equipment type selection, and other parameters, and how do these affect the cost and sustainability. For example, the cost of material, if it is going to be steel, is it going to be carbon steel, or is it going to be stainless steel, or is it going to be platinum? That depends on what kind of operation we have, what kind of safety we have, what kind of reliability we need, and also what chemicals are involved. Obviously, if there is water, the carbon steel cannot be used. Stainless steel need to be used because of corrosion issues. So there are lots of other important things that need to be considered, which are not really included certainly in any software, but the design decisions need to be made. So here is a list of some of the unit operations, and you see what kind of equipment they are, classified as, what type of equipment, and then what are the sizing parameters. So if it is a pressure vessel, it's the diameter length, whether it's vertical or horizontal. If it is a furnace, then the absorbed energy needs to be calculated. Heat exchangers is the area. Compressors, pumps are the brake horsepower, and refrigeration, ton energy removed per hour. So there are different ways to calculate it. So we need models then to calculate them. Some simulators give some of these design parameters. Usually the column diameter length can be obtained as a rating calculation after the simulation. The heat exchanger area can be obtained. So some of these can be obtained from the simulators, others have to be calculated. So the issues are vessels. We have to calculate the diameter length, which is also volume, and the volume is affected by the flow rate, the residence time, vessel type. So you can see that the residence time is very important and the flow rate is very important. Columns, the column profile, what is the vapor flow rate inside the column, what is the liquid flow rate inside the column, how much mixing is taking, what kind of geometry do we have in a plate column or a stage column. All these things will influence the flow rate within the column and therefore the diameter and length. Heat exchangers, again, the flow rates are important, the transfer coefficients, the duties, configuration, pumps, exit flow, exit pressure, flow rate. So all of these are very important and they will affect the cost calculations. Also, we can see that in terms of sizing parameters, if we find a let's say a diameter of a column or a length of a column, what is the lower limit, what is the upper limit? It's not very clear, but if we look at the industrial columns, one could see what is the generally trend of the diameter and length of big or small columns. But if it is smaller than the lower, does it represent a batch operation or is it a continuous operation? Because remember that if the flow rate is small, usually it's a batch operation. And if the flow rate is large, it is not a batch operation, but if it is very large, then are we designing a plant that is going to supply the chemical for the whole world or for a certain region? So these kind of decisions are very important. So unreasonable values should be identified immediately and taken action. Whatever action we take, we have to go back to the design decision, do the simulation, and so on. So that's why if we do it with the reverse design, since in the reverse design, we already take what we want and back calculate out other things, the chances of getting unreasonable values are much smaller. Also, as we know, the synthesis design is an iterative procedure, but we want to avoid as many iterations as possible. So choices of capacity, that is the production rate, what is the hours per year of operation or days per year of operation? Is it going to operate for every day per year or for some days where the plant will be stopped and cleaned or things like that. So those kind of things are very important. What is the temperature? What is the pressure? Because they are related to the safety also. So those decisions are not only just for the mass and energy balance, they also influence the cost, safety, sustainability, and so on. So when we come to point number 3 step, we have done the sizing. Now we want to calculate the cost. We have to select a cost model. You will find in the literature several of them, but most of them start with the Guthrie model. We need to calculate the operational costs. That is the cost of the raw material, cost of the utilities, and so on. We need to calculate the capital cost. That is for the unit operations. And for every unit operation, the purchase cost, and so on. And then we also need to calculate the revenue that we will earn from the sale of products, then determine based on all the costs and the revenue, are we making a profit or a loss? If we are making a profit, then we can do the economic analysis in terms of net present value, break-even point, and things like that. If we are making a loss, we will never make a break-even point. So it doesn't, it's a waste of time to do the economic analysis, but we should look for a profit. And if we are making a loss, that also will point out some hotspots that if we identify the process hotspots and address them, can we make a profit? Additional information also needs to be taken into account are the prices. The prices can change, not only with time, but also with location. The tax, the depreciation of the equipment, interest rate, location, yearly operation period, and many more. So these are also decisions that need to be taken. Once we have done all of that, we can do the analysis. So I will then show you how the analysis is and the concepts for it. If we are doing life cycle assessment, we have to define the system boundary. It is very important what the boundary is. And then we can say that we are going to do the LCA with respect to everything that comes into the system and everything that goes out of the system. Based on what is coming into the system and what is going out of the system, including waste, we will calculate sustainability factors. That is, each factor, subscript J is a factor that can be output minus input, or output divided by input, or input minus output. There are different ways to represent this. And if we know what is coming into the system and what is going out of the system, we can also calculate carbon footprint, ecological footprint, and many more. And you will find at the bottom, the list gives you many different ways to calculate these things. So then we talked about the sustainability index, or SJ. And then we can see with respect to this, how do we calculate these? So these can be also grouped into different types. First is the environmental type. That is related to the atmospheric impact, impact to land, aquatic impact with respect to water, energy, land, material, with respect to economics, with respect to social. So with respect to, let's say, the impacts, if it is negative, you have to see the definition here. So output minus input. If input is bigger than output, then it is negative. If it is negative, it is good. If it is positive, it is bad. So what it means is that because of our process, global warming has increased, so it is bad. Because of our process, if global warming is decreased, then it is good. So if we capture the CO2 and use it without additional CO2 generation, then it will be very good and it will be negative. So we are trying to see that all these impacts should be negative. In the case of material, land, energy, water, we are looking at the ratio. And if the ratio is close to 1, is good. Or if the ratio is low, it is good. If the ratio is greater than 1, it is not good. So we want a ratio close to 1 and lower than 1. For the others, the economics, of course, the profit is, the larger profit we make is good. So that can be good. And the value of the profit and other economic indicators depend very much on the location and the tax and so on. So not everything can be calculated just from the data we have. We need to see other issues, other parameters. And the same goes to the social. For example, because of the plant that we have built in a certain location, how did it improve the society? Do people get better standard of living because of that? Because there is a new plant, more people have jobs. Because of that, there is a school. And because there is a school and more people working, there are more shops. So a lot of these things. Collecting data for these is very difficult. So usually this has to be done separately. And what we assume is that if the other things are good, we are hoping that the social improvements will also take place, because the data collection is very difficult. There is no mathematical models for them. So if we write down some of those metrics, so for example, if you look at the top, total net primary energy used, or total net primary energy used per kilogram of product. So all of these things that you see on the screen can be calculated if we have the simulation results. And then if we have the simulation results, on the left-hand side column, you can see that when we want to do these calculations, we need to, if we have multiple products, we need to say with respect to which product, we will show these matrix. If we have multiple waste, we need to say which is the waste product. We need to identify what is the production rate, kilograms per hour, what is the feed material rate, what is the water demand, what is the energy heating, energy cooling, energy electricity. We can collect all this information from the simulation and from the analysis, from the simulation, from the LCA and so on. And then we can put them into those simple equations to calculate the amount of product per kilogram of raw material. This is a very important number. Amount of energy consumed per kilogram of product. So if we have different alternatives, to compare different alternatives, this is a very good one. Per kilogram of the same product, what is the energy consumed? That can tell us which is the better alternative. So we can do that for amount of energy, electricity and non-electric energy, amount of water used, amount of waste per kilogram of product, and also atom efficiency. Atom efficiency means the atoms that are in the raw material, how much of those atoms go into the product. And if the atom efficiency is good, high, then it means we are using a lot of the raw material waste will be lower. But if the atom efficiency is lower, then we have a low conversion and we are wasting a lot of the atoms that we put into the system. Usually chemical processes have high efficiency. Usually pharmaceutical processes have low atom efficiency. So then once we have this matrix, how do we calculate the impact? Let's say on the left, you see the process. Anything that comes in and anything that goes out in terms of chemicals, we are going to calculate using the equation that you see. I. So I is calculating the impact, and it is going to calculate for inlet and for outlet, and then outlet minus inlet is going to be the impact. Okay, but as I said, it depends on where is the boundary. The boundary can be the plant. The boundary can be also the plant together with the power plant that provides the energy. So it can be misleading if we do not include the power plant, because we can have very nice process with all negative impacts, but when we include the power plant and have the indirect emissions, we will have all positive impacts. So boundary is very important. And then the environmental impacts we will calculate. The top 3 are related to toxicity. The top 4, then global warming, ozone depletion, photochemical potential, acidification potential. At this moment, we can calculate about 29 different properties, but we have not included all of them in the software and on this analysis here. One thing that you see that I have crossed out in red is the total potential environmental impact. I've seen papers where people have taken the summation of different impacts, and then they have tried to make that a single variable environmental impact, and then they minimize that single variable environmental impact. That is totally wrong, because a value for global warming, let's say a value of 10, is not the same as a value of 10 for toxicity. So they cannot be combined together. Also, if we combine them, and let's say our minimum total PEI is 100, I can think of a situation where global warming is 1 and toxicity is 99. So we will save the world with respect to global warming, but we will kill everybody because of toxicity. Or we can take the opposite, that it is still 100, but toxicity is 1 and global warming is 99. So we will save everybody from toxicity, but the Earth will not exist anymore because of global warming. So this is quite dangerous to simplify the environmental impact and sum them together into one. They should not be. One should put upper limits on each of those impacts, and then the optimization should include them as constraints, that none of those impacts should be higher than what is allowed. And then safety, we have used the Dow Chemical Safety Index model, where on the left-hand side, you see the required data. We need to know the heat of reaction, the main reaction, the side reaction, total mass used, construction material, the pressure, the temperature. After that, according to the method, scores are given on the 2 columns. The first column that you see is the chemical inherent index. Every chemical has a value with respect to toxicity, corrosivity, heat of reaction, and so on. And then we count the total number. And on the right, with respect to operation, the operational variables. And then I think the total number is 28 on each case. So the total sum is 56. So safety index of 28 is given in this case. That is the total index, that is all right. And then in each case, we have the inherent chemical safety as 18, and the inherent process safety index is 10. And then if we want to improve, we have to see which of those scores we can improve. If we are using a solvent that is toxic, changing the solvent will improve the toxicity. If there is a chemical that is flammable, changing the chemical will help that. In terms of operational, the pressure, the temperature can help in reducing the number. So a little bit about the software. I will not spend too much time on it, just very briefly. This is the economic analysis tool. starting from whether the process we want to calculate is batch or continuous, then raw material and product, equipment and utilities, capital cost, operating cost, economic evaluation. It provides the pie charts, breaks down the cost, does sensitivity analysis, and compares with alternatives. The LCSoft Toolbox, it has different things in it. I will just highlight two of them. The life cycle inventory, which is needed to calculate the footprint, the CO2 emissions, and the life cycle assessment that helps us to do the impact analysis, the global warming and so on. But it includes a lot of data in it to be able to do those kind of calculations. And the boundary is very important. And as you can see, the input is mass balance, the energy balance, inlet outlet streams. And when we go to the impact calculation, we need the models to calculate those impacts for every chemical. So we also include property models. And then sustainability and safety. The sustainability does two things, that once we have the process and again all the information, it goes into what you see on the middle, the Sustain Pro. It will find out what are the operational paths, and for those operational paths, did a chemical lose its value? Is there more energy used on a path, and things like that. You will see an example that I will show you. And on the extreme left is the safety index. So based on the Dow Chemical Safety Inherent Model scoring, we do the calculations. And then these are all integrated. So starting with ProCFD, then we do the design, we do the process simulation. Then after the process simulation, we generate all the simulation results. That goes into the different tools. And then from the tools, we get the analysis results. And then based on the analysis, we compare and we identify the targets for improvement. So now a little bit about how we identify the target. Let's say we have a chemical process and we have done the cost analysis in terms of purchase cost and utility cost, and we have the pie charts. Obviously, if we want to improve the cost, we should take the big portions of the pie. So if we want to reduce the operating utility cost, the big red part or dark red part is what we want to target. And in the purchase cost, the equipment, the two equipment that has the largest cost. So that's a very simple way of identifying where are the highest costs and how we should, what we should do about that. First is to identify. Then, as I talked about, that there could be open paths and closed paths. I will explain this later. But if we have open paths and closed paths and we can identify them, we can find out whether in these open paths and closed paths, there is a lot of energy used. And then if we are able to find them, then we will be able to identify what to do. So you can see here that if we make this curves with respect to utility cost and carbon footprint, it turns out that the one which has the highest utility cost also has the highest carbon footprint. And then it means that we can identify that this is, for example, a distillation column, and where is the distillation column in the process. And then we will find out that this could be in the open path or closed path. So that's where we will target. So that's how we use this also. So based on this information, we could say that there are some equipment which is using a lot of energy. So we should reduce the energy demand. There is a lot of unit operations. Maybe we should try to see if we can reduce the number of unit operations. We can see that there is a lot of waste of acetic acid. Can we increase the conversion? And so on. So how can we do that? Maybe we can look at hybrid operations, and maybe we can, if we do this hybrid operation, we can improve the sustainability and the LC factors. So, so these give us both the targets and what we want to do. But with respect to the closed path and open path, I will come back to it. And here is where I will explain you what is the open path and closed path. We can say that for a chemical process, we have all the information of the plant. Either we have the plant data or we have simulated. So what is a closed path? If you see the continuous process on the left, the green direction is a closed path because it's a recycle loop. Chemicals and energy is going around in this loop. And if there is a lot of material going around, then it's not good. The open path is the blue line. So chemicals come in, energy come in and go out. And if during this process, a chemical lost its value or energy is going out, we are wasting. So either way, if we can find out whether there is a problem in the recycle loop or in the open path, we can identify the problem very quickly from the simulation results and then say, we have to do something about it. So based on this open path and closed path, we calculate what we call some indicators. So what you see below the table, horizontal green line, those indicators that are above the green line, if they are positive, large positive, it's not good. We need to make them as low as possible. So if the horizontal green line is 0, we need to make it as close as possible to 0, preferably even negative. And those that are below the green line, what we would like them to do is to become greater than 0, as large as possible. So for example, MVA is material value added. If a chemical came in and went out and its value has decreased, then it's not good, because if we want to sell that chemical, we will get less money than what we paid for it. So all the chemical values then have to be larger, as large as possible. So it should not be negative. On the other hand, EWC is the energy that is going around in a recycle loop or in a path. If that energy is very high, it is not good. We need to reduce that. Okay. So as soon as we have the simulation results and identified the open path and closed path, we can calculate this. So how does it work? Here is a chemical process, and you can see some identified open paths. And these are actually the same path, but for different compounds in the system. And you will see the open path if you follow the red arrow. Okay, so now you can see that N-butane, isobutane, 1-butene, and the last compound, they all came in, and when they went out, their material value added decreased. So isobutane is a reactant, and it went out and its value is quite negative large. So what it means is that either we should stop isobutane from going out, or we should increase the purity so that the value MVA is improved. And the same goes for the energy. So that is the MVA, the energy. That what we see is that the energy at this point, that open path for isobutane also carries a lot of energy. And if it is going out with this energy, then we are wasting this energy. We should capture that energy and reuse. So it already tells us this thing. If we look at the closed path, what is a closed path? It is the recycle loop. And you can see the blue arrow. After the distillation, the solvent goes to the absorber. And after the absorber, it goes back to the distillation, because in the absorber, it removes methanol from the absorber and then goes to the distillation column to separate the methanol from the solvent, and the solvent goes back to the absorber. And then we can see that the amount of material going around is quite large. Can we make it lower? So what is negative, we want to make it positive. What is positive, we want to make it as low as possible. So this already gives us the information. So where is the target? These two places are the target. Anything we can do in the recycle loop to reduce the flow rate will decrease the energy. Anything we can do to decrease the flow rate of the chemical going out will improve the MBA. So now we know what to do. And then we have to generate the alternatives. And another way to look at it is that we have the utility cost, we have the skyscraper kind of plot, we have the energy, we have the carbon footprint, and you can see in terms of the energy, there is a cooling heat exchanger, which has a lot of energy being released. But if we look at which are the ones that are contributing to a lot of cost and high carbon footprint, these are the compressor, the heat exchanger before the reactor, and the reboiler duty in the one of the columns, separating benzene and toluene. So automatically we know where is the target, and also it tells us that there is an opportunity to use all the energy that is released by the cooling. We can use it for heating purposes if the temperatures match. So from this information, if we go back to the HDA process, it's not exactly the same process that you will see afterwards, but quite similar. We have the opportunity for heat exchange between heating and cooling, so we can save all that energy. We have identified the locations for the purge, for the reboiler duty, for the pump, and for the compressor. And so the question is, how do we reduce them? So sometimes it is possible, sometimes it is not possible. So for example, in the reactor, can we increase the conversion? Most likely not, because the conversion is fixed by the catalyst and the condition of the catalyst. So we could change the catalyst, but if we use the same catalyst, the conversion cannot be increased. But we can play with the split factor. We can play with the design. So the distillation column design may not give further improvement if it is already operating at the largest driving force. So there are possibilities that can be done, and then we can see if we can find a better solution. Let me skip this and I will discuss it tomorrow. So the final is, how do we represent the alternatives? And I will give you a simple diagram here with only 3 variables. One is representing all the cost, another all the environmental impact, and another waste. What we want to do is to reduce them all. If we reduce them, we will have bigger profit, we will have better environmental health, we will have more resources. How do we achieve this? By reducing the energy consumption, by reducing the water consumption and other consumptions. And how do we achieve them? Through more efficient operation of the system, better design of the process, reduced demand of the utilities. And all of this we can represent in a what is called a radar plot or a spider plot. The green boundary is our reference. Any alternative that we can find which is inside the reference, by definition, is better than the reference and is more sustainable. So what we are looking for are alternatives that are inside the boundary. Any alternative that for one index or more goes outside, then there is a trade-off. We are looking for alternatives that are totally inside the boundary. So representation of alternatives and comparing of alternatives is very important, and this gives a very good picture. So finally, the analysis helps to identify the process hotspots that, when addressed, points to a more sustainable process alternative. And by definition, it will be process hotspots are removed by setting targets for new designs in terms of sustainability factors. We should be looking for non-trade-off solutions. Okay, because we are running a little bit late, what we will do is we will go now to the next section of demonstration and explanation of the demonstration, and then we will take all the questions together. All right. So I will stop the sharing, and Jakrapath and Konkanak will take over to explain the problem solution and the demonstration.